careful about the condition that you need to apply, and then you can think everything is there. Everything is very solid in his notes. Okay? So just remember the power, how to calculate the power. Power is 1 over 2, and then the real part of the V multiplied by the conjugate of I. So this is a very important thing. The average power equals to 1 over 2 multiplied by the real part of the V multiplied by the conjugate of I. Conjugate of current is basically to replace every I with minus I. Okay? So, what else? Okay, I think it's very... So, there's another relationship which is very important. That is the average voltage. Average voltage is this part, and this is incident power, reflective power. Right. Reflective power, that is reflection coefficient, has a power of 2. Okay, so there's tough stuff. So what is the power delivered to the load? PL. So what is power over here? Just remember, right now, so what is the power delivered to the load PL? Because right now we have a lossless transmission line. So the power over here is exactly the power at this point. Okay? So at once you can calculate the power here, and then you can get power that is at the load. Then if you want to know the power here, then you should need to know I or Z or V. And how to calculate the corresponding impedance, voltage, and current, I have mentioned before. Like, do I need to repeat? Okay, you use the telegraph equation again to calculate the ZI, that is the impedance at this point. After you know the impedance at this point, then you can calculate the current at this point. That is, you use the voltage multiplied by the overall impedance. Right? So it is, I want to know the current here. So the current here is the voltage of this whole circuit, and then divided by the impedance here. So that is the I. Then I can get the PL equals to PI. So that is at this point. Then at this point is 1 over I square Z. Alright? So then you can calculate. This is to use I squared Z. Then to use the voltage, it is 1 over 2 voltage square multiplied by Z. Is it? Yeah, just be careful about where to put the real part. Where to put the real part. This is to use the real part of Z, not the real part of I. They are completely different things. Okay? So for the transmission line part, just be careful with the calculations. And be very familiar with the calculators. So this is another lifestyle. Oh, you have a quarter wavelength transmission line terminated in CL. So you just substitute L with lambda over 4, and then you have ZL, then you can calculate this part. So after you have a quarter wavelength transmission line, then the Z in over here can be just calculated by the square of characteristic impedance divided by ZL. Right? This is maybe a conclusion to you, but for our engineers, when we want to do our impedance matching, we can use this. Okay, I'm not going to say too much about it. So this is calculations. So this one has just a summary of many important concepts. What is gamma L and how to calculate the SWR, standing wave ratio. Okay, standing wave ratio. So it's basically you see like this, or whether your wave is like this. Okay. Is it damping too much, or is it just a very smooth wave? quarter wave transform. Oh, this one will be tested as well. Impedance matching, this one. Impedance matching. So, I think I've mentioned about this. So, why we need impedance matching is I write it over here, right? Yeah. We want to transmit as much power as we can. So, we want no reflection. So, the reflection coefficient should be 0. What is the condition for the gamma to be 0? That is, the ZL should be the same as Z naught. That is the same as long as the network that I have right now has the characteristic impedance, which is the same as Z naught, then the power will all be transmitted without any reflection. That is the reason why we need to do the impedance matching, to match the impedance, to make my impedance at this point to be equal to Z naught. Okay? So, in short, impedance matching is to make your impedance at this point to be equal to Z naught. And when you equal to Z naught, then VSWR will be 1. There will be no voltage peaks on transmission line. Okay? So let's see. This example is a very classic example to show the concepts of impedance matching. So it has let's see. A signal generator needs to feed equal power through a lossless 50 ohm transmission line to two separate resistive loads of 64 ohm and 25 ohm at a frequency of 10 megahertz. Quarter wave transformers are used to match the loads. You see, there's a quarter wave transformers. You guys read about this? Quarter wave. I skipped this.
Lambda over 4.
Yeah. Lambda over 4 is a very magic number for transmission line length, because when the transmission line has a lambda over 4 length, then it has a very special characteristics. Okay, so again, use the telegraph equations with the L substituted by lambda over 4. You can calculate ZQ squared over RL. So that is, it's basically basically to say this is your transmission line, and this is your Z in. This one is ZL. As long as this one is lambda over 4 with the characteristics impedance of Z naught, then the Z in I observed at this part is going to be Z. Yeah. Right? Okay. This is the one. So if right now that I want to, so why this is very important, because right now that I ask you to make your Z in to be 75 ohm. Okay. And I have, and I have the load, that is this part. So at this part, I want this to be 75 ohm. But right now, the load that I have is 100 ohm, which is a settled number, which is a set number. I cannot change this, I cannot change this. So the only thing I can change is Z naught. Then, if I want to match them, I need to apply a quarter wavelength transmission line with characteristic impedance of Z naught. Okay. Right? Any question about this? Again, so the transmission line length is a quarter wavelength. When you have a quarter wavelength transmission line, then I can have this equation. This equation is important for you to do the impedance matching. And I give you an example. Right now, I ask you to match the whole circuit to 75 ohm. That is to say, in this equation, the Z in is 75. And right now, here, the Z load is 100 ohm. So ZL here is 100 ohm, which I cannot change these two. So I can use this equation to calculate Z naught. Okay? So this is 75 and this is 100, and then I can calculate them. So I can calculate Z naught. So that is to say, after using this. Right now, if I'm asked to match this circuit to a 75 ohm, then I need to provide a quarter wavelength transmission line with characteristic impedance of this number. Okay, so that is how this things looks like. Now, quarter wavelength transformer are used to match the loads to the 50 ohm line as shown below, right? To match the 50 ohm line, that is to say, this one is 50 ohm. Now, the first question is determine the required characteristic impedance, that is Z0, and the physical length of the quarter wavelength lines, assuming the phase velocity of the wave traveling on this half speed of light. So, determine the required Z0. Required Z0. So in this case, we have so let's observe what is happening over here. Now you have a transmission line of characteristic impedance of 50 ohms. So this one is 50 ohm, okay? And now you have shunt two antennas. So first antenna is, and they all have a quarter wavelength. So one antenna over here, this is quarter wavelength. This is antenna 1. So this is 64. CL is 64 ohm. And there's another one. This is DL2 equals to 25 ohm, with also a lambda over 4. Okay? So this is how your circuits look like. This is antenna 1 and antenna 2. Then determine the Z0. So that is this one. This is Z01. This is Z02. Okay? Like I mentioned over here, if I know the left part and I know the right part, then I can know the central part. Okay? So the central part is the square root of Z in dot ZL. So if I want to match them, the left part is Z01 equals to Z in 1 multiplied by ZL1, right? So Z in 1 is 50, right? 50.
Yeah.
Because I want to match to 50. So Z in 1 is 50 and ZL1 is 64. This is how you calculate Z01. That is to say, this is how you calculate the characteristic impedance of the quarter wavelength transmission line used here in order to do the impedance matching to the 50 ohm. Similarly, you can also do it here. So how to calculate Z02? Z02 is Z into multiplied by ZL2. That is this one. Okay? So this is basically the answer to the first question, the required characteristic impedance. Also, the physical length of the quarter wavelength lines, assuming the phase velocity of the waves traveling on them is half to the speed of light. So physical length, that is to say we need to know the lambda. Because the length is lambda over 4, so we need to know the lambda in this case. The lambda in this case is so the lambda equals to 2 pi over k, right? 2 pi over k, that is up equals to omega over k, right? The phase velocity equals to the omega over k. So the k equals to omega over mu phase velocity, right? So this part is 2 pi over omega over phase velocity. this is 2 pi, omega is 2 pi f, and this one is 2 pi, right? So the lambda equals to u phase velocity over f. Right, so this one is 0.5 speed of light, and f equals to
10 hertz. 10 megahertz. 10 omega hertz.
10 megahertz, right? 10 megahertz. So you can just calculate the wavelength. Then don't forget to divide it by 4. Okay. So the second question is find the standing wave ratios on the matching line sections. Standing wave ratio. Standing wave ratio is VSWR, or you can call SWR. So it is 1 plus gamma, 1 minus gamma, right? So it's plus and minus. So why is absent? Oh, guys, we made a mistake. Because we want to match to the 50 ohm. So here is 50 ohm. But because they are parallel, so for each part is 100 ohm. If I match these to 100 and this one to 100, then I have two parallel 100 ohm, which gives you a series 50 ohm. If I match them to 50 and I match them to 50, then the 50 is parallel, then it gives you 25 ohm here, then this one is not matched. So that is to say, this part is 100, and this part is 100. Okay? Be careful about this. So, see, the Z in 1 and Z in 2 are both 100. They are parallel, so I cannot make them to match to 50 individually. So, this one is very straightforward. On the matching line section.